Hello and welcome to the Better Software Conference 2025. Today's talk is by me, Bill Hall, and it's going to be on tools of the trade. So firstly, who I am. I am Bill Hall, commonly known by my moniker online as gingerBill. You can probably guess why. I'm also the creator and main architect of the Odin programming language, a programming language which is for modern systems. It's a systems level language, and it's effectively a C alternative for the joy of programming. I started working on this about 9 years ago, and wow, how far has it come? And I'm also currently working with and at Django Effects on numerous different projects, such as Embergen, which is our real-time volumetric smoke and fire simulation software, which is used throughout the game, film, and TV industry, mostly games at the moment. We also have GeoGen, which is our real-time terrain generation software. We also have LiquidGen, which is our real-time volumetric liquid generation software, and Illugen, which is our real-time procedural animation generation software and many other things specifically tailored for game developers. And also in general, my general background is in quantum mechanics, specifically in quantum metrology. So I was dealing and developing things such as quantum clocks and quantum gravimeters back in the past. But now I'm a full-time programmer instead. Also, whilst I note, you may have noticed this is a recording and I'm not actually at the conference. Unfortunately, I was meant to be there, but I had to have an appendectomy to get rid of my appendix. So unfortunately, I'm now recovering at home and not in lovely Sweden. So I'm sorry I've not had to be there. So I hope the conference is absolutely wonderful at the moment and everything is going well. So shall we get hit on? So first, why are we all here? Right, what is the whole point of this conference? What is the main thing that drives us to even be here? And I think I can sum it up in one word: craftsmanship. Fundamentally, we're all here for that thing. We honestly care about our work. It's the first thing we have to do, right? We care about what we are doing. We care what we put out to users. And pardon my French, we don't want to put out shit. We want to put out good quality stuff that works. We see the enshittification of software and how software is getting worse and worse and worse every single day. Software that is effectively the same functionality as it was 20 years ago, it's like Microsoft Word, and it has virtually no more functionality it is, but it's so much slower, so much worse, so much buggier. Everything is worse about it, right? And it's like, okay, what else does it do nowadays? Oh yeah, nothing really. It just may look a little bit prettier nowadays, but it works worse. This has not benefiting anyone. It's all because the people who are programming this stuff don't care, pretty much. And the people they're being managed by don't care or anything. All of it, throughout the lane, they don't care about the thing that they're selling. And they can get away with it. That's the problem. They get away with it. But that's the thing. We're here at the Better Software Conference because we want to produce better software for people to use. Fundamentally. That's why we're here. But the other thing that's also a little bit more specific to us as well is that we actually care about the hardware that software is ran on, right? This isn't some abstract thing. We aren't pretending that, oh, we don't know what we're running on half the time. You usually pretty much always know what the hardware you're running on. So why don't we just actually understand and make our software work for that rather than some abstract machine that doesn't really exist? Again, all of this is craftsmanship, and we strive to be better at our craft. So before I even started with my talk, I wanted to do a little bit of showcase of some of the software from some of the speakers at this talk right now. And this is just a small selection of some of the ones that I like the most, pretty much, just to keep it small. I don't want to go on for hours. So the very first one I wanted to talk about is from Andrew Rees, who's a very good friend of mine, but it's Whitebox. As he would summarize it, is to watch how your code behaves as you write it. Whitebox, for people who have never used it or seen it before, please try the link on there. It's whitebox.systems. It's effectively, if you think of a debugger, of an visual debugger, it's more than just that. It will track the data as you are programming through it and seeing how it modifies and see how it evolves and so on and so forth. This is one of the best pieces of software I've seen for programmers to visualize what is actually happening on with their program. This is the first step, in my opinion, towards proper visual programming. And it's something which I have not ever seen properly done, especially on a generic case where it'll work with your C and C++ code out there. The next one is from Vyacheslav, and I apologize, I can't pronounce your surname, but this is called FilePilot. Now, most people who have ever used Windows probably use the File Explorer, obviously, because everyone probably uses it as the most used application on your actual computer, most likely. And you know, nowadays with Windows, it gets worse and worse with every single version update. And the File Explorer is no different. In fact, it is so bad now and so slow and so buggy, and it crashes all the time. And Microsoft again don't care. They don't care. But VXLab has cared and actually tried to make an alternative. And not just that, this is engineered from scratch, from the bottom up, to be not just feature parity, but so much better. It has so many more features, so many more functionality, and just again, so much faster. And a tiny little executable, which is, I can't even remember, it's only like a megabyte or a few megabytes in size. It's tiny. And it does so much more than the bloated Windows File Explorer. So please check it out on filepilot.tech. There's also the project by a good friend again from Ryan Fleury, which is the Rad Debugger project. Now, he works at Rad Game Tools, which is now owned by Epic Games, but specifically he's working on a brand new native user mode graphical debugger. Currently, it's only working on Windows, but there are plans, and they're going to be soon. Again, at the time of the recording, it's not available, but it's going to be working on Linux and Mac. So this video on the side here, you can probably see, on the left is him building the Rad debug from scratch, then debugging a programming in it, and already started. Well before the time that even Visual Studio has even gotten off past its splash screen. This is showing you how slow stuff, even Microsoft's tooling is. Like Visual Studio is that bad and that bad slow, that if you can compile the entire debugger, and by the way, if they do pretty much the same amount of features, if not, Rad Debugger does even more nowadays, because especially with what it's being capable of with all its visualization tools, it's there. There's also, as part of the tool, because it's been debugging, they've created their own new Rad linker, right? A new linker which is faster than anything else available on Windows, and it's already been used in numerous games on the by the Epic Games, obviously. Fortnite is the one that I can think that is the most prominently used by this already. And lastly, I'm just going to showcase myself, which is again the Odin programming language. This is 9 years of my life now at the time of recording, and yeah, I wanted an alternative to using C++ because I was getting so fed up of those languages, and at the time there was no alternative for a manual memory management language, which that was kind of in the imperative procedural domain. There wasn't, so I had to go create my own, and thank goodness that I have. Not just people at Django Effects, where we have over 24 employees now, and half of them are using Odin on a daily basis. But Odin is being used by tens of thousands, if not hundreds of thousands of people. It's a bit surreal, I will tell you that. Something that I started on a very weird night, let's put it that way, and it's now gone here. So if you want to check out Odin, please go to odinlang.org, and then you can try it out for yourself. So, firstly, okay, we're all here because of craftsmanship, great, but why this selection of people? Why does all of this exist? And it's because of one thing. It's called Handmade Hero. Handmade Hero was an ongoing project by Casey Muratori about nearly 11 years ago, and the whole point was to create a professional quality game from scratch with accompanying videos where he explains every single line of code he writes, and also made the source code available for a little bit of a price, but you could also just watch the videos for free, and they will stream live on Twitch and then upload it to YouTube. And again, the text from the trailer was what captivated us. When I saw this trailer, I went, yeah, that's what I want. And it was just like, oh, wow. And I'm just going to just quote it here to begin with, because even in the trailer, it's silent. When I was little, games were made from scratch by people who loved them. There were no license engines. Every pixely little hero was coded by hand. My 30 years of game programming were inspired by this way of life, and I believe it is worth passing on. So I am starting the project to help preserve it. And that man again is Casey Muratori. So for people who don't know who he is, also, hello Casey, welcome to the Better Software Conference. He is a programmer who has been specialized in game development and game engine research over numerous years. He's worked on many projects at Rad Game Tools, such as Granny and Bing 2, and he's also worked on games such as The Witness, made by Jonathan Blow. And beyond Handmade Hero, which I've just talked about, he is known for popularizing many different concepts, such as immediate mode graphical user interfaces, which are very popular nowadays. The N-way linear quaternion blending, which is effectively, instead of using S-lerp, spherical lerping, he would just do normal lerping and then normalizing over the top, and it works out pretty damn well. He also is very good for popularizing, implementing the GJK algorithm, which is very mainly used for like collision detection with shapes. But most recently, he has been doing a numerous Substack series on computer enhance. This is effectively explaining the internals and lower levels of how computers work and how to deal with that as a programmer, and actually better. So I highly recommend checking out all of these links. Again, the link to this slide is available I'll tell you at the end of this presentation. But I don't want to just talk about this. I want to say that look, Casey Muratori changed my life pretty much, right? And I think he changed the life of so many people at this conference right now. The entirety of Handmade Hero made me reevaluate how I was programming in the first place. He effectively kicked me out of this very dogmatic way of thinking. Like I was just following the people who I thought were experts, and he just went, no, start thinking for yourself. And then I started questioning. I was like, oh wow, I was actually going, oh, this isn't common wisdom what I'm learning. It's common just things. It's Chinese whispers. It doesn't mean it's actually good. And again, it reinvigorated this self-reliance, so that when I was as a programmer, I would get so much better. And again, clearly we're all here because a lot of us made a community around this series, and the general lessons that we learned from it, and the general ethos that we had, this handmade ethos that we started calling it. But that's been 10 years now, maybe nearly 11 years of my life, and I've made some very good friends along the way, and I've started a career and from it as well. Like Django Effects is effectively people, the initial people. In fact, most of us are people who know about the Handmade Hero series and came around from that. And we're not alone. There are many other people and companies that are because of that. And I just want to say thank you, Casey. Thank you so much. And I bet there's so many people in the audience right now and people watching who just want to thank you for everything that you've done. Thank you. So let's get on with the talk, shall we now? Let's talk about the tools of the trade. This is the name of my talk, and you'll understand why I've framed it this way to begin with. So when people think tools of the trade, specifically in programming, usually the first thing they may be thinking is, oh, the computer I'm using right now. I'm using particularly a MacBook Pro as my laptop computer at the moment. Or they might think, I need a better, they're talking about the keyboard or the mouse or the display. A lot of this, again, these are tools that you're using to program, obviously, and use everything like that, because your computer is a tool. The keyboard might be, but a lot of these maybe also, like, you could put them in like the mouse and the keyboard they use and the display. This is maybe more ergonomics than general tools. But again, ergonomics are important, but not the topic. You may be thinking a bit more abstractly and going to software. I'm not going to hardware, go software. Maybe thinking, oh, it's the text editor I use, or the IDE, or whatever it is they use to program. That's the tools of the trade. And I'm like, yes, they are. Okay, should we go a little bit further down? Okay, no, it's the debuggers I use. It's the tooling around that to actually understand how my code is working and such. Yeah, that's a tool, obviously. You may be even a bit more, no, it's actually the languages I use and the compilers I use, or any of those sort of things. It's like, okay, again, that's still software, we're still getting there. I'm saying, like, okay, we're going to go a little bit more abstract still. The next level of abstraction could be, it's algorithms and data structures. And I like, okay, many people who know me, I love Niklas Wiert's book, Algorithms plus Data Structures equals Programs. And I think it's a very good way of understanding what a programming is, conceptualizing it as those two things, algorithms and data structures. But again, it's abstract still. It's not, you implement those and they're still kind of general abstract entities. But like, look, there's something that most of you in this audience, in fact, most people in general, neglect. And they even forget that it's a tool, it's an abstract tool, the thing that we need to have in our metaphorical toolbox. And that thing is mathematics. Yep, all you people, you're going, oh no, mathematics, this is a maths talk, isn't it? I'm like, yes, welcome. Yes, it is. But Before I start, I want to say, look, there's a lot of lies we tell ourselves and others, especially specifically about mathematics. Like the first one, when many people try and get people into programming, we always say, oh, you don't need much mathematical knowledge to learn programming. Firstly, that's like just a lie. You need at least arithmetic and algebra, right? And also technically modular arithmetic. But most people know that, right? Good example of modular arithmetic is your watch, and that's effectively mod 12. But like there's some loads of things about mathematics, because again, a lot of people say they don't know this because they don't really know what maths is or mathematics in general. The other one is that, oh, you don't need that much mathematical knowledge to program well in the first place. Again, yes, you do. You may not need enough to start making your own first, I don't know, terminal app or something like that. But as soon as you start to make any more complicated program, you will need it, right? Make a game, you'll need to learn, I know, linear algebra at a minimum. Okay, you're making some accounting software. Great. You need some more, like, okay, general arithmetic. You may even need to know some accounting. You may need to know loads more mathematics. It's like, okay. All of this is like, whatever you're doing, you still need mathematics. And you need to be good at it. The other one is sometimes people tell themselves is like, oh, I can learn as we go along, right? I'll learn it when I need it. And that's, yeah, that gets you quite far, to be honest with you, right? Makes you may be good. It doesn't mean you're going to be great. It fundamentally is, how do you know you don't need it unless you know it exists? Because there's a lot of areas of mathematics that people don't even know anything about. So how are you going to learn it if you can't even come across it? And lastly, there's a lot of people will go, oh, well, I was never good at mathematics at school, so I'm just not going to learn it. This weird arrogance and this arrogant ignorance that people have. It's like, you don't care about your craft, really? Just look, you're programmers, right? There's a lot of things, even at school, people will always ask this question of, oh, when am I ever going to learn this, sir? When am I going to need to learn this thing that I need to know? I don't think I'll ever need it. I think it's for many people, they'll do. But you're a bunch of programmers. So you're going to need a lot of this. So stop pretending that you're just the average man down the street. You're not. We're going to start learning. So I'm going to try to teach you by an example that you have a set of skills that you need to learn, right? And there is no excuse. So again, warning, there will be mathematical notation, but throughout that you can understand what the message is going to be, right? So firstly, the topics I'm going to cover anyway, I'm going to talk about some calculus, specifically discrete integrators. That's what we're going to actually finalize at, by the way. And the next is going to be linear algebra, and specifically how matrices and graphs might be related somehow. But again, this is the important lesson. This is the thing I'm going to try and get through to you. What I'm going to do today is not a lesson. I'm not going to teach you these things. I am just there to give you an overview of mathematical topics that I expect most of you in the audience and watching at home know nothing about, most of you. And the main objective is for you to know and go out there and learn more mathematics to broaden this mathematical toolbox, to add more tools to it, these mathematical tools, so you can become better at your craft. Again, this is not me going to teach you it. I'm just going to show that most people, you don't need to know enough. And again, I don't. I need to learn more mathematics myself as well, because it never stops. And when I learn more stuff, I can find more uses for it, even when I was in program, like, wow, I wish I knew that sooner, because that would have solved this problem, this problem, this problem. But how are you going to know? So let's start with the first one, shall we? Calculus. Specifically, we're going to do something called lerp smoothing. So this came about when I was talking to, again, my friend Ryan Flurry just over 2 years ago, and he was doing this kind of lerp smoothing in one of his, I think it was a game I think he was doing. So lerp smoothing, for people who don't know, is effectively, if you've heard of lerps, this is linear interpolation, by the way, you're going from one point to another. And the lerp smoothing is effectively, as you get closer and closer to the target, it'll slows down, but you're moving towards a target. So the dumb approach most people do, as you can see the code here on the left, is you have A equals the lerp between A and B of K. Now, if we expand this out, this is what the code looks like, really, right? You've got A plus B minus A times K. That's effectively what this code is doing. And if you know got a plus there, we can do the a plus equals b minus a times k. Now, let's play this little animation to explain what this does. So you notice as it gets to the target, it gets slower, and then once I get near the end, I just switch back. But what you may notice is this isn't frame rate dependent. All of these here are running at different frame rates. So the one on the left is my native, and then it's cut by half, a third, fourth, fifth, sixth, right? And it's not frame rate dependent whatsoever. At different frame rates, they're going to be doing different things at different times. So many people in the audience have probably heard something about like the delta time. That's the time between the current frame and the previous frame. And they've always learned, that's like, oh, if you multiply it by dt, magically things get themselves fixed, right? So let's try that, shall we? Let's just try that little animation. And if you look at it, it is slightly better. But we'll just leave it to run for a little bit, a few seconds. And notice it's starting to drift still. So yes, that dt thing, times in by the delta time, is a good approximation. But again, it's still subtly frame rate dependent still, right? But the question is, why? I thought times in by dt was the solution, right? Well, in this case, it's not. So that times by dt is what many people in mathematics and physics calls an ansatz. Ansatz is a German word. Effectively, it's the tool currently in place, right? And we're going to use this as a starting place tool. So I'm now using mathematical notation. That a plus equals thing has now been written here as the delta a. That's the plus equals saying the change in a. That's what delta means. The b, which is your target, minus the current a, times by some k, which is your constant, times delta t, right? That is where we're starting from. That's what we think the answer should look like, because it kind of did look correct initially, and then it started to drift. So if we put the delta t onto the other side, divide by the other side by delta t, we get a delta a over delta t now equals this equation. Now, for people in the audience who already know this, they would go, wait a minute, that looks like a differential equation. And that's right. So if we change those deltas into d's, we have now got a differential equation. So this is this technical term for it is a first order, which means there's only one differential, d by dt, that's it. And it's linear, means there's only a coupling of a term in there. Ordinary differential equation, right? So ordinary rather than partial. That's all those words, fancy words mean, but that's what we've got here. Now, when you have got a differential equation, you want to usually solve it to find out what the actual equation is. Now, I'm not going to go through integration to say how to do this by hand. One of the tools in your toolbox as a mathematician we have nowadays isn't just pen and paper and your mind. We have tools like Wolfram Alpha, a brilliant, beautiful tool I highly recommend most people check out. And effectively, I just typed in that equation and got the solution. And it told me that that equation, a of t, so a as a function of time, can be expressed best as this case. So it's equal to b plus some constant times e to the negative kt. So this is e is the Euler number and the power of. So it's the exponent of negative kt. That is what we've got here. Now, this is effectively the general solution to our ansatz, is what we call our kind of educated guess. Now, it's in a form because we've got this C1, this first constant. We don't really know what that means. So if we actually solve it knowing that the A0, so at time equals 0, our equation should equal what the initial A value is. So if we rearrange it, we actually get it into this form here, right? A of t equals a of t times e to the negative t plus b of times 1 minus e to the negative tt. And when you do that, some of you in the audience will go, wait a minute, that's a lerp. And it is a lerp, in fact. So we started off with a lerp, and now we've got a new lerp, right? But again, this is still not what we wanted, because we wanted this discrete differential form, so we can just keep adding increment to on each iteration, right? Rather than having the perfect generalized solution. So if we rearrange it to get it into a form that kind of looks similar to what we had, it'll look like the following, right? You got that a plus the b minus a times this new term. So we notice this new lerp parameter has this 1 minus e to the negative kt, right? It's not just the kt anymore. It's this 1 minus e to the negative kt. So it's a little bit fancier. But it's still not the incremental form. So the way to do that is we need to just replace the t's with delta t's. So if we start with all this, we start at a naught, and then this is what differentiation is, by the way. You make these small little parts, you make a little bit of a chunk, and you start off this delta t, and you put that in all the valuation, we get this delta t. Now, we're starting from the 0 point, but that was arbitrary. We evaluated everything at a0. It was an arbitrary thing, and we're going to know that it will hold for all a. So that upside down a means for all, right? So thus, we get this solution here. So the change in a is equal to b minus a times 1 minus e to the negative k delta t, right? That's our solution. That is actually the solution to what we started with. Now, this makes it more frame rate independent. But why does it look so different to the original equation? Because we just had k delta t initially. Why is it now got this exponential function in here, and it's like there's negatives, and it just looks different, right? What's going on? Well, there's a trick, which many people may not know, is that you need to know something called like the Taylor series. This is what you can do when you expand the function that you have around a point. In this particular case, we're doing it around 0, and seeing how we can express it in terms of a polynomial. And it turns out that 1 minus e to the negative kt, when you expand it out, starts with a kt, k times delta t, minus k delta t squared over 2, plus k delta t cubed over 6, minus, and so on and so forth. Right? So this is how we expand it and turn it to a polynomial. Now, because we're doing this for people who want to know in the audience, this is when you evaluate a Taylor series around 0, it's sometimes called a Maclaurin series, named after the Scottish mathematician Colin Maclaurin. Yes, that's his real name, Colin Maclaurin. It does roll off the tongue quite nicely, but yeah. But usually in general, we'll call these Taylor series because we can then generalize it so we can evaluate at any point, not just 0. So if we plot that Taylor series and replace that exponential and put the Taylor series in there, we can start to see that our original guess, our original ansatz, was just an approximation of a lower order equation, right? So we effectively had that k delta t plus higher order terms. So the square terms, the cube terms, the quartic terms, and so on and so forth. So if we just understand that, we can understand why our guess was pretty good initially. It's just as time went on, those higher order terms were not being added to the contributions, so they started adding in more and more errors, right? So if we look at back into our final code, we just replace that k dt part term with the 1 minus the exponent of negative k times dt. Or if you want to expand it out, not use the exponential function, you could just add all those extra terms in manual if you wanted, up until the point where you say, that's good enough. So we've actually got a nice solution to this problem. We're already there, right? So here's our improved form, and I'm going to start the animations for it, shall we? And you can see these have got the things 120 hertz, then it goes to 60, 48, 30, 24, 20, and it's much nicer. It's not drifting as much, but we do have a slight issue. We've got, looks like a 2 regime problem here. So the ones above 30 hertz are kind of grouped together, and the ones below 30 hertz and below are kind of grouped together as well. So there's no this tilting drifting we've had anymore, which is great, by the way, but there is this 2 regime system. 2 regime system is actually an artifact of how I've kind of written the code, but also they aren't fixed frame rates. So that's the reason why it's the case. You can fix it if you take that into account, but I wanted to keep these examples pretty simple, so I wasn't trying to cheat too much, right? But that's great. So why is this new method much more stable? Well, if you actually plot what that comparison, that k delta t term compared to that exponent term, you get to see it. So at the higher frame rates, like 144 hertz, 120 hertz, look, it's like 0.2, 0.3, 0.4% difference between the numbers. All right. But as you get lower and lower frame rates, the difference is big. So even at 10 frames per second, that difference is now 5%. So after 10 frames, you're about 50 odd percent out. And then after 100 frames, so in that case, 10 seconds, you're more than 5 or even 6 times out. It's compound interest at that point. And it just gets worse and worse with the errors. So if you can minimize those errors by having a better method, oh my goodness, just do it. And it will just be a much better thing. But again, you may want the simpler method, again, but you need to understand what errors and costs you're taking into account when you do it. Notice this difference is per iteration, not in total, because again, it compounds and compounds. That's why it starts diverging. That's why it does looks like a seesaw as it goes up and down anymore, slopes rather than keeping in track. But here's the thing, there's a lot of people shouting in the audience already telling me, why don't you fix your time step? Well, the thing is, that's fine. Fixing the time step is a good solution if and only if you never change how much that time step is fixed to, right? Because if you need to change it and you actually change the logic, that might be fine. You may think, oh, I'm going to just fix my time step to 60 hertz. But now it's like, great, now you support the logic 60 hertz, but a lot of people have monitors now which are well above 60 hertz. Again, for the display I'm working at the moment, it's 120. I want at home, I have is 144. I know many people now who even have 240 or even higher. So if you're fixing your logic to a frame rate that's lower than the refresh rate of the monitor, you're going to start seeing those stutters quite easily. So when you do to a lower fixed time step, things are going to start looking weirder as well. But again, if you're doing the correct integration in the first place, rather than fixing it to fix this again, add a bit of determinism, you can get a lot of help to get the correct answer in the first place. And just relying on that fixed time step is fundamentally a bodge, right? Do not bodge your code if you don't have to. That is kind of the message for this entire thing as well, man. Don't bodge your code if you don't have to. So, but even then, we're going to still show you the fixed time step approach. Now, I'm going to make the time step 6,000 hertz. So updates 6,000 times thing. And they're going to show them across the different frame rates. And this is generally the effect of the code we have here. This is just Odin code, but slightly same thing. And you can see it looks pretty nice already. It's pretty smooth across all different frame rates. But again, we have this two regimes thing still happening. But in general, we don't have this diagonal drifting that we had previously. But again, it's still, fixing the time step still doesn't fix all of your problems. You're still going to get some other ones. And noticing even at the different frame rates, it's still going a little bit weird. And there are reasons for that as well, by the way. It's not a mistake. There are reasons for it. Again, this is exercise for the people at home to know. So, we're going to think about other methods. So the thing is about what the approach that we just done today, effectively, is a specific type of a discrete integrator. Now, you may be asking, oh, does the approach that we've just touched always work? And the answer is no, it doesn't always. Because the equation you may have may be very hard to figure out. It might not always be impossible, it just might be very hard, or it may be a little bit more complicated and requires a little bit more instability. Technically, the one we've had here is technically a form of a forward Euler method, and specifically, it's actually a special case of a first order exponential integrator, because it was exponential in that case. Now, exponential integrators had loads of research going on since the 60s, but in general, they have their own issues as well. Now, if you're dealing to make your own physics simulator or something like that, the forward Euler method does have its issues, but there are improvements. So you may want to do forward and backward Euler methods. You may want to do the Runge-Kutta methods. So you can have more, again, the whole point of these methods is to have better stability or better compromises or whatever they're meant to do. So again, I highly recommend you go research more about this on all of these topics, because you will learn a lot more about the shortcomings, the trade-offs, and the benefits of all of these different ways of doing things. And finally, I'm just going to start with something a little more complicated, just to show you what if things are really complicated. Like, for instance, what if our B value that we're trying to smoothly lerp towards keeps changing, right? It's not a constant. Well, when you integrate this, it gets a lot more complicated, right? We start from our ansatz, and then we find the actual solution from the ansatz. We get this really complicated differential equation, which is still like unsolved because we don't know what B is. So if we plop in what B is to our equation, like say B is a sine function, just keeps going up and down, that's all it does, then we actually get this really complicated solution, right? We could have guessed at what it was when we put them into the equation. We could have just said this was a sine and then think this was good enough for our ansatz. And the answer is, looking at it, no, it's not. So going from our ansatz and then putting in the actual solution gives us something a hell of a lot more complicated than we realized. And you can see how much it's going to drift even further off than from our starting position. This is why it's always good to actually show, okay, what is the real solution, the actual solution to our problem, and what's a good approximation. And or not even a good approximation, what's just an guess. Sometimes it's like we need to get closer to the real one, and I like that. So hopefully this is the idea of why we're doing some of these animations, and knowing the mathematics that you're doing, it helps to know calculus, because this is all calculus I'm doing, right, at the end of the day, but you're making it so you can make a better product that works correctly. Again, do not botch. So that's the first part of the mathematical section I want to talk about, right? If you've got any questions, please contact me at any time. Just that's it. But again, the second part I want to talk about was linear algebra. When I was planning to do this talk, I was having a lot of people ask me effectively two things. Like, oh, could you do something on linear algebra? And some people saying, well, could you do a thing on graph theory as well? And then I thought, okay, these people don't understand there's a relationship between these two. In fact, there is a direct relationship between matrices and graphs, right? In fact, these two things here, right? The matrix on the left, and the graph on the right represent the exact same thing, in fact. So, and you go, some people go, oh, okay, obviously that makes sense. And then some people go, does it? Right? So to explain what a graph is at the end of the day, for people who may not know, graph is kind of has all these edges, and these are directed edges with weights on them. So that's what the numbers represent. And they've also got these nodes, that's the green dots are for. And that these edges are pointing towards the different green dots to show a relationship. Now the matrix is a little bit more abstract. It just has numbers in a 2D array. So what's going on? So for people in the audience who can probably already guess, if you notice that the column 0, the first column, corresponds to the outgoing edges from a node. In this particular case, it is the vertex 0, the node vertex. You'll hear node and vertex interchanging most of the time, right? So again, that 0.6 is representing as the going back to itself. The 4 is represents from the vertex 0 to vertex 1, and 0 is not on there because there's no way of going from vertex 0 to vertex 2. Now note, by the way, the convention I'm using here is a column major convention. That's because I want to put the matrix operation on the left, applying to some vector, some other thing on the right, right? Some people you'll see in some textbooks, they'll use row major convention. Again, it doesn't really matter which one you use. It's just a convention, right? And I'm just trying to be consistent with what I'm using. Now, the other thing you may have noticed is if you look at the rows, right? Those incoming edges that row now represents the incoming edges to the first node. So the 0.6 that is pointing to itself, we've got 0.7 going to that node, and then another 0.6 going to the other node. So hopefully the colors here, for again, the orange, blue, and red, make it clear. So that's kind of how you notice, oh, that graph is now represented with this matrix. Now, to make it even clearer, I can show you those columns with those vertices, again, V0, V1, V2, how they are related to the matrix. Such. Now, this relationship between the matrix and a graph has a name, and that matrix is called an adjacency matrix. Again, it's showing you what the adjacent nodes are with their connections with it. Now, you may be asking, okay, great, but what's the use of this? Because it just looks like some okay, it's a nice little trick, but is it useful? And the answer is extremely so. Another way of looking at this is I've just changed the graph here, and I've just changed the numbers on it as well. And I'm doing this now to represent them be probabilities, right? So now these nodes, those outcoming nodes, are effectively representing probabilities of going from one node to another, right? And how it traverses from going from one node to another. So that matrix is what we call a Markov chain. This is the matrix now, the matrix form of that a Markov chain. So this is really great for understanding. Markov chains are very useful to understand going between different states in a machine. Now, a good example of this is maybe in a game, right? You've got different states in your game, and they have different probabilities of moving from one state to another, right? And if you can express it in just probabilities, like, okay, I'm starting from this state for my hero, and it's like, oh, there's a chance if I roll a die, it goes to this state or that state, right? And if you can figure out they're all different states and they can connect to different things, that's called a Markov chain. Another example is you could have a very bad, but it would work actually, by the way, a very bad system for knowing the weather. You could say these three states here, V0 is it's sunny, V1 is raining, and V2 is cloudy, right? Just say that's the simplest weather state you've got possible. Makes sense for England, right? So for V0, if it's currently sunny, there's a 60% chance that it's going to be sunny again tomorrow. But there's a 40% chance it's going to start raining, right? And then when we get to the raining state, there's a 30% chance it's now going to go cloudy the next day, or there's a 70% chance it's going to be sunny again. Or if we're in this cloudy state, that means there's an 80% chance it's now going to rain tomorrow, or there's a 20% chance it's going to be sunny, right? That's kind of thing. You can understand these dynamics by looking at these probabilities. So you can look at this matrix, and that matrix effectively represents this walk. That's what I'm going between all these vertices, these nodes, as we go through the graph. So because it's just a matrix, we can apply it to a vector. So let's say we're starting from vertex 0, that's definitely the probability of 1. We apply the matrix once, we get the probabilities we expect. There's a 60% chance that we're in the V0 state, 40% chance we're in the V1 state, and a 0% chance we're in the V2 state. So that's great. Then the next question is, what if we apply M2, the matrix, twice? So we have 2 steps going through that iteration. Well, now we know it's 64% chance in V0, it's 24% chance in V1, and a 12% chance in V2. Okay, what if we do it 3 times? Well, again, we now know all the distributions where we do. So if we started from, again, V0, after 3 steps of walking through this probabilistic graph, we now know there's a chance, again, 57.6% in V0, 35.2% in V1, and a 7.2% chance in V2, right? That's how this could work. And that makes a lot of sense. However, what if we actually did this infinite amount of times, that we kept stepping through this infinitely? Well, we actually find that this tends to actually a nice distribution. In fact, it's 9 30 seconds, 10 30 seconds, and 3 30 seconds in those distributions. And this place where we tend towards, after infinite, it could even be finite, by the way, but we're saying infinite in this case. This is called our steady state vector. Now, to make it clear, not all graphs have a steady state. The most trivialist one I can think of is, let's say you've got 2 states and they just ping pong back and forth between them. Like each state goes, this one, now this one, this one, now this one. There's never going to be a steady state because each one, they have effectively the same equal probability, but each state's going to be different each time. But again, this is very fine. So, but if we look at what this steady state means, mathematically speaking, it's effectively saying if we apply our Markov chain, our walk, the matrix, to the steady state, we get the steady state back. We don't change, right? That's what that means. But again, if we rearrange it into a more conventional form, we can find, like, okay, if we have the matrix minus the identities, that's the 1, 1, 1, all the diagonals, 0 everywhere else, and then multiply it by the steady state, we get 0. The 0 matrix. Yeah? That's effectively what is going on. And it's very, how do I put this? A very interesting thing to note. So you could have a game, it's a good example of this, and you've actually, a lot of games can be expressed in spreadsheets, and that's how a lot of game designers do. They have a giant spreadsheet with all the probabilities, all the things. You could compute this and actually find out maybe there's a distribution that you're aiming for, even if you play these numerous games, or if you're trying to make it balanced or something. This is what you're going to have to look out for, right? You're going to have to look at what happens with these. If you're doing a probabilistic, effectively finite state machine like this, where does it all tend to? Is there a steady state, or is there not? You might not want a steady state. You may want something that's not steady. You may want something that's pinging back and forth. It depends on what the game mechanics you're doing. Say it's a game. But the thing is, what I've just kind of showed you is actually something called eigenvectors. You may not have known this. You may have heard of this term before. You may have not. This is the thing, right? Eigenvectors are something that kind of get briefly talked about in many linear algebra courses. But that steady state is a specific special case of an eigenvector. In fact, it is technically the eigenvector that is represented by the eigenvalue that's equal to 1. So that's a bit of a thing. But to know what this means here, to show the eigenvector, it's like you have your matrix, you times it by the eigenvector, let's call it V. That is equal to some lambda, the eigenvalue, times by that vector. So it's some scaling parameter, right? Now, this is a very useful thing to know in a lot of mathematics. Eigenvectors and eigenvalues are effectively these things which effectively map to themselves with some scaling value. That's very, very useful to know. And again, a steady state vector is a good example of this. Now, to be very careful, not all eigenvectors represent a steady state. It's not the same thing. In fact, to get a steady state in this property, there's a very particular case. It means you have to have an eigenvalue that is equal to 1, and all of the other eigenvalues, if they exist, obviously, but all the other ones have to be less, have to have their absolute value be less than 1, right? That's what that means. Now, again, not all matrices that have an eigenvalue of 1 mean apply steady state. They have to have all the rest be less than 1 in absolute values. But that's effectively kind of what it is. It's a mapping to itself. If it's something where you apply this matrix to a vector, you effectively get the vector back with a scaling. That's all that does. So that's a nice thing to know about. Again, it's a little bit of a topic, and I'm not trying to teach you what it is or how to even derive them. I highly recommend you read them up, but that's just more of a, this is what exists, and they're actually pretty useful. So let's go on to connections, right? So there's another thing about graphs. So if you have a directed graph, which is again, they're going from these nodes, and then they've got directions on the edges. If you can go from one node to every other node in the graph, and they all can go to connect to each other, we call this graph strongly connected, right? That means we can go from any state to any other state with some chance, maybe a probability or a certain weight or whatever. Now, if they cannot do that, for instance, you can go from, let's say, node 1 to node 7, but node 7 can never get back to 1. This is what we call a not a strongly connected graph in fact. So the bottom one's a good example of this. Like, for instance, let's say the nodes on the left do get to the nodes on the right, but the nodes on the right can never get back to the nodes on the left. In fact, there's that just big long arrow. There's not one that goes backwards. You're stuck. Now you may ask, why am I bringing this up? Why is this useful? Well, it is. So there's something about this. So if you have a strongly connected graph, the matrix that represents that graph is what we call irreducible, right? And this means that all matrices that have non-negative parameters, weights in them, by the way, most of this I'm talking about is non-negative weights, but it doesn't matter, are reducible. So I've made it to make it this simple. I've said all the weights are just 1 in this particular case, just to make it easier. But in general, this is what is going on. And this is just to show you, okay, this is a matrix, and this is effectively the irreducible, the simplest form we can represent this graph in. Right? That's effectively what this means. You go, okay. But what if the matrix is reducible? Like, it means, okay, that means you can split them apart, make it into something else. You can go like, oh, look at this graph here. One side, one part of it is strongly connected. All those nodes can connect to each other. And the other part of the graph is also strongly connected. And then there's this weakly connecting edge connecting these two subgraphs, these strongly connected components together. So when you're thinking about it, you could actually describe both of these matrices. You can reduce them into irreducible graphs or irreducible matrices. That's kind of the point. So now you can start thinking them in isolation. So when you look at this giant matrix, I've numbered them here. So 1, 2, 3, 4, 5, and 6. You can represent it with this matrix. Now it's just full of ones and zeros, but it's still not easy to explain unless someone's noticing a pattern. There is a pattern to this madness, right? It's because it's matrices within matrices, man. Let's refresh that. There we go. Technology. I love web browsers and their consistent rendering. But as you can note here, is that this top left-hand corner, the orange one, is the components within that the edges within that first component. The blue one is the edges within the second component. The bottom left-hand one is showing that one edge. There's only a single one in there, which represents going from the edges from the first component to the second component. And then finally, there's that top right, which is a bunch of zeros, because you can't go back to the first. So effectively, you've now got a bunch of zeros, which you can just ignore, right? That's something that helped you do your algorithms. And you go, okay, well, again, why is this useful? Well, before we go there, it's again, if you're asking this question, why is it useful? Why is it useful? Again, it's missing the point. This is tools in your toolbox. You don't know when you're going to know the use, but you might do, and you'll see why. So we've just rearranged this into this form. So we now have got effectively a bunch of matrices, but the top right-hand corner is just zeros, right? This has got a technical term. It's called, I'm going to probably get rid of this name wrong. I'm sorry. It's the Frobenius. I'm sorry. I can't do Prussian names. I apologize. He's dead, so I don't think he's going to be offended. But there's this Prussian mathematician, and he was kind of in this normal form. It's called a Frobenius normal form. Some people, you may hear it in some textbooks called as the rational canonical form, or whatever. Effectively, is what you've got is a giant matrix where literally half of it is just a bunch of zeros, and then the rest of it is representing all of the irreducible submatrices or the subgraphs, those strongly connected things. And that's kind of how you're showing it. So you now actually demonstrate this all of here and go, oh, you split it into smaller little things and smaller or strongly connected graphs. So then you can also analyze them together or on their own. So you can actually see a bigger picture of nothing. One of the reasons why you're doing this is that you're not trying to, well, sometimes it's compression, but sometimes it's just not overfitting too much when you're trying to analyze these graphs. And it's very useful, but I'm going to stop, right? And there's a reason why I'm about to stop. Because once you've got to this point here, right, that's understanding you can represent these graphs as matrices, represent them as, split them down to smaller matrices and smaller big graphs and rearrange them and all this, we can actually go into different parts and discuss completely different things. So I just started showing that there was a relationship between matrices and graphs. Okay, great. So what could this beginning of this talk actually been? Well, it could have been welcome to game AI, which I was kind of briefly talking about with all of these Markov chains and such, right? That's one place we could have started and then talked about all that for a while. Another one is welcome to machine learning. Seriously, this is actually a beginning step when you learn about machine learning, because that Frobenius form is great. That's really useful so you do not effectively overmap on your models. Things don't get overrepresented all the time. And you go, okay, so these things we can ignore completely, but these things are the important part. And also we know the relationships between these parts. And maybe you can maybe do shortcuts, just cut things out, or just showing the general patterns of what are going on with the machine learning, right? This is a really useful thing. Or it could be something else. Or also another thing was this, welcome to traffic analysis. This is how traffic analysis, because again, these nodes could be traffic lights, the cars moving through them, the rates that they're doing. Like this is actually what a lot of civil engineers are doing. Well done, you've now done civil engineering, but I could have started from there. It could have been, welcome to mesh topology. You go, wait, what? Yeah, so when you're representing meshes in games and such, or not games, just like any 3D software, they're represented as nodes and edges. In fact, you many hear things like half edge meshes out there, or you may have what's the other one I'm thinking of? Radial edge meshes as well, right? But you have all these vertices, you'll have these edges, you'll have these loops, you'll have faces. These are half edges, the loops are, and you have all these different things built together, but they're all just different types of nodes with different edges connecting all their relationships together. And then you may want to do analysis on this, see if you can actually break apart meshes, see where they're strongly connected and weakly connected, wherever, and then just do the stuff. Well done. You've now just done some mesh topology. But that's the whole point, right? This is the point. If you know your tools, you can then go and go, oh, I can learn these new fields, or actually, I'm working in this field. This is actually really useful for me, right? Look, and this is the thing, is once you start learning more and more mathematics, there's an endless number of fields that you can apply this in programming to. And this is why I stopped in a very weird middle place, because I'm like, look, we could have gone to so many different areas. We could have gone to geometry, right? That was effectively done algebraic graph theory or algebraic geometry. We could have gone to traffic analysis, get machine learning, AI, whatever you want it to be. But that's where we're getting to. And this is why it's so useful for people to know mathematics, because you don't know what you're doing, right? If you don't know it exists, you don't even know you could do it. But this is the beauty of it. Like, this is the beauty of learning mathematics in general, because it opens up so many different things for you that you didn't even imagine. And that's kind of where we've got to, right? like I've covered so many different topics. Like I've talked about looking about ansatz, these are educated guesses, differential equations, integration, Taylor series, fixed time steps, numerical integrators, and so many other things in just the first half. And the second half was like matrices, directed graphs, weighted graphs, Markov chains, eigenvalues, eigenvectors, matrices, irreducibility, Frobenius form, normal form, whatever you want to call it, or it's text special case of Jacobian normal form as well. But like, there's so much here. Look, the more you know, the more you can apply it to, and the more you're able to do. That is fundamentally, I want to try and get across in this entire thing. Learn some mathematics. You'll be a better programmer for it, and you will improve. So, thank you for listening to this talk with me. From me, Bill Hall, or gingerBill as most know. You can contact me on Twitter, also known as X, at the gingerBill, or go to my website, gingerbill.org, or my email, which is bill@gingerbill.org. You can view these slides on my website at bsc2025.gingerbill.org. So if you have any questions, please contact me. And again, thank you very much, everyone at the Better Software Conference 2025. And thank you for letting me have this talk. And thank you very much, and goodbye.
Okay, so Bill, I thought it'd be funnier if you have to sort of pick questions from people yourself, because it's like, oh, that guy in the back there.
Yeah, that guy there, please. Right there, please. No, yeah. Squinting, trying to get seats like those.
So who do you want?
I'll take the guy with his hand. And,
yeah, Taylor, what's your question?
I can try and yell really loud. Can you hear me?
Just, yes.
So one of the things I find hard about mathematics is a lot of the concepts are named after mathematicians in the past, so various names, various country names, or from various dialects and whatnot, right? So they're often very hard to remember. As opposed to computer science, the names are often coming from regular linguistic words, right? Do you think that that is, I guess, something that is just, you have to get around, you have to get used to learning people's names and how to pronounce them, or could it be useful to rename these things with more like simple language, I guess, or something like that?
Oh, good question. The thing is, computer science, a lot of things are still named after people, like Dijkstra's method. Many algorithms are named after people. However, in most fields, things are named after the people that discovered them. Computer science is just the weird one. So I know it's sometimes hard to always remember the names, and I struggle as well. And as I said in there, the Frobenius form has got the rational canonical form is another name for it as well. But again, this is still not simple language. Mathematicians are some of the worst people for naming things, even worse than programmers. And the best way to get it around it is just don't remember the names, just remember the pattern, and then try and work backwards. But if you want to learn the names, usually sometimes the way I've always done it is learn the story for that person about how they discovered it and such like that. Same with when it came to physics. I can remember some of the famous physicists by their names because of a story. Like, for instance, I don't know if it's Kepler or Tycho Brahe or Newton or Maxwell or something like that. I remember the stories of their life and then kind of know what it is. So it's kind of more of a historical biography for me than the actual physics. I know that sounds weird, but that's the way I can sometimes remember it. I'll take the guy on the left with his hand up. I don't know which one. I'm going to point to him.
Oh, John. So you don't want the doctor? There's a doctor on the right.
I know there's a doctor in the crowd. We're just picking random
John,
at the moment.
John.
So thank you for the talk. I love these like high-level overviews because they help you navigate. Because my problem, I mean, I have a great appreciation for math, but I'm not great at it, right? And it's hard for me to penetrate math concepts because usually I find them so convoluted. But when you give me these pieces like, oh, look, this is this, and this is that, and that is that, it helps me immensely to penetrate the content because I know stuff, but I can't connect it. Like, do you have any like good resources? Like, because if I go to Wikipedia and read about math, I drown. Oh man, right? But like, what's your resources, right? Or does it get better, right?
Oh, okay. You're going to hate this. I never can recommend resources to people. I agree with Wikipedia. So Wikipedia is usually the worst resource to learn anything from because it's not meant to be, right? Wikipedia is written for people who've already got a PhD in that topic and just want a refresher on it. That is pretty much what Wikipedia is written as, and it is great for those types of people. It is awful to actually learn from. For many of these topics, it's hard to find out where the best resources are. So for stuff like the linear algebra, stuff like that, I would recommend getting a book on physics, physics and engineers book. Like one of the good mathematics books I had when I was doing my degrees was literally mathematics for physicists and engineers. It was a great book. It was very practical. It was literally like a doorstop, about 3 inches thick. But it went through all the different concepts and it just showed you all of them and gave you a load of examples to work through. As you get into other concepts, for instance, maybe let's say the graph theory stuff. Interestingly, on the graph theory stuff, some of that you may actually try different areas of mathematics. So this will sound very weird, but it will make sense in a minute. When you're doing graph theory, you can try and do it as abstractly as possible, and you'll learn about colorings of graphs and all this lot. Or you can go into, again, gambling. And then this will sound bizarre. I don't even enjoy it, but what I mean is that a lot of games like this and gambling games like this are actually, this is how they do it. They're cheating. They're trying to find out where the distributions are so they can always have an advantage. So sometimes learning a field that uses it and then finding the books on that topic are the best way of finding it. So I can't really give you any specific resources because unfortunately, as you guessed by that talk, it was a tangent followed by a tangent followed by a tangent and it was all over the place. That's how my mind works in general. So I'm probably the worst person to give you a resource for. So I'm sorry about that. But literally pick a topic, find the areas in that field, all the books on it, and then just keep doing that and you'll eventually get this scatterbrain like myself.
Thank you.
Can we do the doctor now? The surgeon?
Well, I basically had
Hello.
more or less. Hi, Bill. More or less, I had the same question actually. Like, yes, I was inspired by this talk, and now I want to learn about math. My first and only resource is Wikipedia, because the other resource would be to actually apply for a university degree and then do the courses. Because I can't find anything in between of how to solve that besides, well, like I said, practical problems. But that's how people do it, by learning okay, I learn it on the way. Because that's, I think, the only way I know of learning about those mathematical concepts.
And you already went to school to become a surgeon, right? So
This is beyond. You should have studied physics. Yes.
No, but yeah, again, I think the point here is when I say learn a random topic, I mean literally learn something. Like, for instance, I taught myself some game theory once. So I was at university course and I took a game theory course, even though it was not related to what I was doing. And from that, I learnt linear programming, which is constraint solving. And you think, why would that have anything to do with game theory? And the answer is, it's actually just constraints at the end of the day. You have most games, basic like non-zero sum games and such like this, they're all just bunch of constraints. You put them into a giant matrix and then you solve it with a simplex method. Simplex method is a way to solve linear systems usually. And it's like, okay, I really, when I learned this, I went, oh my goodness, this is now, I could have used this anywhere in programming, but I just didn't know it. But that's kind of the thing is, when I say learn as much as you can, literally learn as much as you can everywhere you can. Try and be a polymath, a renaissance man. I don't know, whatever you want to call it, but I'm not, I know that's, you'll be surprised what you'll find is what I'm trying to say. And this, again, I can't tell you, oh, read this book, because that's not even how I learned. And I know also talking about university courses, you'll be surprised. Most universities, or not most, a lot of universities will tell you what books they are recommending and what courses are. The thing you're paying for at the end of the day is that piece of paper. Also, many universities, if they're open campuses, you can just walk in and audit them. Like, seriously, you can just do that. I used to do that for courses when I was at university. I used to go in music classes. I did a physics degree. I wasn't doing music. But I used to walk in and just audit them. And the thing is, and again, this is a fun fact, most lecturers and professors don't care. You just sit in them. You're not taking the exam at the end. Maybe, I don't know if that's technically bad advice I'm giving you, but it's probably, it should work. Right.
Bill?
Anyone else for the questions?
there is one.
Oh, okay. Yes, I can see.
Terry.
Do you have any opinion on geometric algebra for game development?
Just don't bother. I went down the rabbit hole of just generalized abstract algebra in general. So GR algebra and like Clifford algebras and all that stuff in general years ago. And my eventual answer to this was, it's not that useful. It's just another way of thinking about things. But if you're thinking about, oh, this would be really useful because you now unified the entire algebra in this Clifford algebra, which is what 3 spatial, 1 temp, time, and then all the other stuff on top. It doesn't actually make it harder. You just now got loads more different operators to worry about. And when you actually deal like with physics, they still keep the basic vector calculus stuff that you're doing everywhere, and then they do it very piecemeal wise, because in general those are the operations you're doing. Now, if you do the geometric stuff, yes, it looks more elegant, but the mathematics that you're going to do at the end of the day will be the same thing. It's the same computation. All it does is it may look more fancier to you and then make it completely obtuse to everyone else on your team who can't read it. So it is the balancing act of, are you doing this because it's actually going to be useful for you, or are you doing this because you think it's cool? Remember, you're a bunch of programmers, so this is not cool. Right.
Oh, we
Yes,
got many
you got the front.
questions now.
Or back
Andrew?
or wherever.
Maybe a silly question on one of the specific topics. With the LERP example,
Yes.
we started with a difference from time equals 0 and then changed that into an incremental algorithm. And it seems to be that the incremental part of that was what caused the error to accumulate.
Correct.
How do you feel about, like, do you have any general thoughts on this kind of incremental algorithm versus trying to do the total solve from a particular point in time? So like just doing the t equals 0 from the time when the animation started rather than accumulating each.
If you can do it, then do it. If you can do the actual calculation, like you know the exact time it's working from, then do it that way. The thing is, a lot of stuff, if you're doing like physics simulation, for example, again, the talk previously was doing that in many cases, they're integrators. You don't necessarily know what's going to happen, but you know, like we say, the differential equation, that you know how the state evolves as it goes times on. You just don't know the full state of the system. Sometimes you have to do an integrator. You have to integrate, literally add every single frame. But if you have the beauty, the luxury to have this, we know we can actually just put a time in, do that. This example I did was literally because I remember on the Molly Rockets forums about over 2 years ago, I was speaking to Ryan, and Ryan was doing it. I just derived it and I went, here you go, here's the frame rate independent form of it. And it's just one of those, but sometimes that's what you've got to do. And again, physics simulations, anything that's differential equation, by pretty much most of the world can be derived in differential equations. That's what a physicist will tell you, obviously, but it's kind of true. And most of the time you cannot know the whole state. You can only know the local like changes in that state. And that's pretty much how the universe works anyway. Like you can only know the local space and literally how that evolves. You can't just know the giant equation for everything. Not even God knows that. So that's a better way of putting it.
John, you had another question? Unless Taylor wants to go first.
So you swapped between like notation you might see in a programming language over to mathematics and then back to a programming language.
Yes.
Notation. Do you think there's room for getting our, like, whether it be the text editor or various tooling to have like typesetting for mathematics inside the programming language, or at least in comments or side text or something like that?
There are text plugins that already do this, especially for like LaTeX, I remember around, so it's already doing that. So they usually do it just in the comments. So if you make sure you do like the dollar sign, then it will do it within them. But so that's already a plugin thing, and it's quite useful if you want to actually explain it. But I don't think it should be within the actual code itself. This will sound weird, but especially if we're I was showing it imperative procedural code, obviously. I don't think that should be trying to be blended into mathematics and use all the fancy symbols, even if you could, just because how you're conceptualizing that is very different to how most of the things work. So you can't, for me at least, this is just me, I like that distinction between the things. So I can have like a context switch, change the hat that I'm working on for the different things. But yes, it is sometimes nicer to blend it, but it's a different trade-offs. This becomes a language design problem at that point, and then it's like, imperative procedural programming has been solved since the 60s, and there's not much that's going to change now, unless you create a complete new paradigm, which I doubt is going to happen anytime soon.
Follow-up question: would you rather the variable names be named after the mathematical terms rather than like whatever makes sense in a programming sense?
No, so this is actually a thing I absolutely hate about mathematicians who become programmers, is when they literally just do the DA, that's literally one character symbols. And this is a lot of times why people hate shadowing so much in languages, let's say imperative languages, because it's like a lot of these people using like one letter things. sometimes it's fine. Like, okay, dt is very common convention, say, oh, actually delta time. But please, I'd rather have a literal paragraph than you just use some arcane, like, oh, this is Z. Like, what does Z mean? Well, Z is actually the decay constant for the blah, blah, blah. But it's like, just write the decay constant for the blah, blah, please. Just write that out. You've got fingers, you can type it. You're not, this is the thing that people forget, is that mathematicians like short things because they're manipulating symbols on paper a lot of the time. You're programmers. You've got your 10 digits, you're typing on a keyboard, you can manipulate it as, you're not manipulating it like that. It's a very different way of thinking and different domain entirely. So just type things out, you're reading it. It's not manipulation.
Okay, we have time for one final question before we go on break. Somebody have the one final question to end all questions. Vladimir.
There we go. Guy at the top.
Does the mathematical universe map well to the actual computer? For example, in the lerp example you gave, right, you're integrating over real numbers, you're using all these theorems, and so you're sacrificing some amount of rigor when you go and translate that into Ryan's like float32 code. So is that just in general not a problem? Like you can just...
Oh no, it is a problem. So first off, rigor, you're talking to a physicist. I'll bodge anything usually. But it's... The thing is you do, if you know floating point, you know it's not real numbers, right? Reals and floats, they've always got things to have to take into account. And you have to know what the precision on those floats are when you're dealing with them. So when you're doing, like, again, we do fluid simulations at work, right? A lot of the time we're trying to just keep them into 16-bit floats everywhere on the GPU. We're doing this because we want to minimize bandwidth and also maximize the amount of space, VRAM that we're trying to use, GPU RAM. The problem is, we do also get, it works faster, but you've got less precision. So you have to also worry about, okay, so how are you going to do the operations to minimize those errors as well? So you've got all of these things on top. So you see, it doesn't map to the real world. It's like, well, floats are their own weird thing that you have to consider and understand how they work. So you have to kind of have this own mental model of how they operate. And again, in a mathematical sense, they're not rigorous, right? Because they've got things in them called nans. They're not a number. So they're not reals in the first place. So it's kind of, you've got all this. If someone tried to mathematically describe floats, they'd struggle a lot, is what I'm trying to say. But you have to kind of think like, yes, you got this not idealized sense, but you've got this set of mathematics, then you're applying it to the real world, and then you can say, oh, there's actually these problems here. Like engineers have to do this, by the way, as well. It's not just programmers have this issue. Even if you don't have floating point, things are fudgy. At the end of the day, you're going to have errors in your measurements everywhere because every measurement you have has an error associated with it. You can't get around that. There's nothing perfect. So you always have to figure out what your tolerances are, what's acceptable, and just how to just know the constraints of your problem fundamentally. Like what is the tool that you use, the platform you're using, whatever it is. It doesn't have to be floats. It could just be integers and the issues with them, or float fixed point in arithmetic, or whatever on top. Hopefully that answers your question.
Okay, with that, so we're about to go on break, and then I want us to come back at 1:15 for Vyachoslav's talk. Can we get another round of applause for Bill?
Thank you very much. Yeah. Well, thank you very much for having me. Anyway, and have a nice break.